In this video, I want to discuss the relationship that SO3, the group of rotations or orientation preserving rotations in three-dimensional space, is topologically the same as the manifold RP3. And I feel like usually when people discuss this, they go through like quaternions or SU2 or even maybe in Clifford algebras. I feel like that's just too much machinery. There's like a very direct way to see this, which is very nice and elegant and sort of uses the special geometry of three-dimensional space in order to see it. Okay, so in order to show this, let's try and sort of parameterize SO3. So maybe as a warm-up, we can look at what SO2 is. And to specify an element of SO2, in other words, a rotation in the plane, all we need to do is specify some angle. And so we can see that we can parameterize angles by the unit circle. And for every angle, in other words, any point on the unit circle, this corresponds to a unique element of SO2, which says rotate by that amount. And so we see that SO2 is topologically the same as the circle, because if you sort of move a little bit on the circle, then that corresponds to moving to nearby rotations. Okay, so how can we describe rotations in three-dimensional space? Well, what's the data that you need to rotate in three-dimensional space? Well, because of, in general, when you talk about rotations, it's actually rotations in a plane. But because of the special geometry of three-dimensional space, we have that any plane has a unique perpendicular vector. So in order to specify rotation in three-dimensional space, all you need to do is specify some direction and specify some magnitude by which you're rotating about that direction. And so this is encapsulated by the data of taking some vector v and specifying some angle theta. And without loss of generality, we can take v to be a unit vector. And so what this says is that you pick the direction v and then rotate by the angle theta around v, and this uniquely determines some rotation in R3. So we have a map from this data to SO3. Now, we want to find some sort of a space which uniquely parameterizes points in SO3. In other words, a one-to-one correspondence. Here we have a map going this way, but if we have an element of SO3, can we uniquely determine vector v and angle theta? So one thing is that you can determine the vector v by looking at the fixed axis of any rotation, and there always will be a fixed axis because you're rotating in a plane. And so you can have a uniquely determined unit vector, except it's actually uniquely determined up to sign, because you can either have v or minus v. But I'll mention that a bit later, I guess. And your angle theta, you can rotate from 0 to 2 pi, right? But what you can do is you can say, okay, if I'm going to rotate from 0 to pi, in other words, from the stationary position to 180 degrees, I'll consider this vector. But if I'm going to rotate more than 180 degrees, then instead, something more than 180 degrees in this direction is the same as something less than 180 degrees in the opposite direction. So what we can do is we can encapsulate this data by looking at the vector theta v. And now I'll restrict theta to lying within 0, pi. And so what that means is that we'll only look to rotations up to 180 degrees, but that's okay, because if you want to rotate by more than 180 degrees, we can just rotate by the antipodal vector. And theta v will take values inside the unit ball centered at the origin of radius pi. So what this says is that in three-dimensional space, we have this unit ball of radius pi. And if we take any point over here, this will uniquely determine a rotation. And what that rotation is take this vector, rotate around that vector counterclockwise by the magnitude of that vector. And this way we don't have the issue of saying like, oh, you can either rotate around like this vector or this vector. And that's because if you rotate by less than 180, if you restrict your rotation to being less than 180 degrees, then by dictating that you rotate counterclockwise, that uniquely determines the direction of the vector as well. Except this does not quite uniquely determine a one-to-one correspondence between the unit ball and SO3. And that's because if you look at v comma pi, in other words, rotating about this vector by 180 degrees, or rotating about this vector by 180 degrees, then this is the same as minus v comma minus pi. So in other words, if you rotate by 180 degrees in some plane, then that's the same thing as rotating negative 180 degrees in that plane. And So that means is that these two opposite points of the unit ball of radius pi should actually be identified. So what that means is that SO3 topologically, and the reason that this is topological is because if you sort of move the axis about which you're rotating a little bit, or you change the angle by which you're rotating a little bit, both of these are sort of continuously varying changes of continuously varying families of rotations of R3. So that means is that SO3 is homeomorphic to the unit ball with the equivalence relation that P is to be identified with minus P on the boundary of the unit ball of radius pi, which you can think of as the unit sphere of radius pi as the boundary of the sphere. And only the antipodal points have to be identified on the boundary because, as I said, anywhere inside the boundary, since you're rotating by less than 100 degrees, that uniquely determines whether you're talking about the v direction or the negative v direction. Okay, so this is essentially a 3-disk modded out by the boundary of the 3-disk, or not exactly like that, but P is equal to minus P on the boundary of the 3-disk. And you might recognize this as being the description of RP3. And if you don't recognize this as a description of RP3, you can think of it as like this. So RP2, we can describe it as the unit sphere with opposite points identified. But by we can sort of get rid of the lower hemisphere and just consider the upper hemisphere. And now any point on the interior of the upper hemisphere corresponds to a unique point on RP2. But any point on the boundary circle, you have to identify opposite points. And so similarly, you can think of the interior of the 3 ball as being sort of the upper hemisphere of the 3-dimensional sphere in R4. And then this boundary will be the boundary sphere, similar to how this is like the boundary circle. And we have to identify opposite points, and then we get RP3 directly. Okay, so we've just shown that SO3 is homeomorphic to RP3. And so what are some consequences? Well, we now know that pi1 of SO3 is equal to pi1 of RP3, which is equal to Z mod 2. And the reason for that is that RP3 has a universal cover, which is the 3-sphere. And because that's a 2-fold cover and the 3-sphere is simply connected, that tells us that pi1 is Z mod 2. And it turns out that the universal cover can always be made into a Lie group. And so we can define some Lie group called spin 3, which is the universal cover of SO3, at least topologically. And the way that you make this into a group is that an element of spin 3 will be some path from the identity, which will take us the base point of SO3, to some element G. And if we had some other path to some element H, then we can compose gamma and gamma prime by multiplying gamma prime by G, and then we'll get some other path going from G to GH. So it'll be G times gamma prime. And then if we compose these two paths, then it'll give us some path from E to GH, and this is the multiplication on spin 3. Remember that you can define the universal cover as a space of paths from the base point to some other points, or a homotopy cluster of paths. So this is sort of like a way to nicely define spin 3, which is the universal cover of SO3 as a group. And because the universal cover of RP3 is the 3-sphere, this will also be homeomorphic to the 3-sphere. Another really nice description of spin 3, which I won't go over right now, is the space of unit quaternions. And it turns out that these descriptions can be related to one another. Another consequence of this is that you can show that pi1 of SON is equal to Z mod 2 for n greater than or equal to 3. But for this, I guess you need to know a little bit of homotopy theory. So the idea is that we have that SON acts on the unit sphere Sn, and it acts on it by just rotating. And if we look at some point P in Sn, then the stabilizer of the point P is going to be SON minus 1. And the reason is that it essentially corresponds to all rotations which are orthogonal or keep that point fixed, which means that you rotate the orthogonal sphere, which is n minus 1 dimensional. So you can pretty easily see that on the 2-dimensional sphere. So what that means is if we fix some point P in Sn, then we have a map from SON to Sn, which sends some element G to whatever G sends P to. And this in fact defines a fiber bundle, which has fiber SON minus 1 to SON down to Sn, which means that this is a map of spaces such that the preimage of any point here is a copy of this space. So you can think of this as sort of like a smooth generalization of the orbit stabilizer theorem, where this is the stabilizer and this is the orbit of the action here on Sn of the point P. And I recommend you to sort of like work out the examples for maybe SO2 and SO3 directly and see how this works out. But now from this, we get a long exact sequence of homotopy groups. So we have pi1 of SON maps to pi1 of Sn, maps from pi1 of SON minus 1, and this gets a map from pi1 of, or pi2 of Sn. And now, because we're assuming n is greater than or equal to 3, we know that pi2 of Sn is equal to 0 for all n greater than or equal to 3, and also pi1 of Sn is also equal to 0 for the same thing. And so that tells you that pi1 of SON and pi1 of SON minus 1 must be isomorphic because the two ends of this exact sequence are both 0. And this concludes that pi1 of SON is equal to z mod 2 for n greater than or equal to 3. So what that means is that you can, similar to this description, even though we don't have something like the unit quaternions here, you can define a group spin n, which is the universal cover of SON. In case you're wondering why these are called the spin groups, it's because this is essentially, one way to interpret this is like this is what gives rise to spin. So in physics, you have something called spinors, which are reps of, I guess, complex representations of the Lie algebra SON. And this doesn't correspond to the Lie group SON because this is not simply connected, but this is simply connected. So this it corresponds in one-to-one correspondence to the representations of the Lie group spin n. And so this is why you have some sort of a weird object where if you rotate it by 360 once, then it doesn't come back to itself. But if you rotate it twice, then it does. And you don't have a phenomenon where like you have to rotate it 3 times to get back to itself because SON has fundamental group of only order 2. If it were to have something of like order 3, then maybe you could have something where you rotate 3 times and then get back to itself. But you can't because spin n is the universal cover and it's just a 2-shade cover of this.